Hi, I'm Martin Wells and I'm a Research Fellow at the John de Laeter Centre at Curtin University. For this presentation, I will be talking about some of the main findings of the recently published Merrower M532 report. However, before I continue, on behalf of my co-authors, I would like to thank the project sponsors Merrower, Demers, Lithium Australia and Rio Tinto and the many individuals and companies who contributed to this work. Due to the scope and breadth of the project, I will only touch on a few highlights of the research. First, I'll provide some context to the project and touch on the project's scope and objectives before we look at some of the research findings. As I think we're all aware by now, lithium is one of the key elements in lithium-ion batteries used in our electronic devices and in hybrid electric vehicles. The predicted increase in demand for lithium in clean energy applications will need about 40 times more lithium by 2040 than produced in 2020. In helping to meet this demand, in 2021, the WA lithium industry produced just over half of the world's lithium output. However, while there are a few reports and publications of individual pegmatites, there hasn't been a comparative study of LCT pegmatites across WA. So there is a somewhat limited knowledge of the lithium mineralogy of pegmatites. And as more deposits are coming into production, there is the growing realization that pegmatites are more mineralogically and texturally complex than previously appreciated. So a question you can ask is, what is the impact of these mineral textural variations to the processing and recovery of lithium? So the Merrower M532 project was initiated in 2019 with the aim of addressing these questions. The overarching goal was the development of a geometallurgical framework for WA lithium pegmatite deposits. Research was conducted in 3 modules and focused on deposit geology, mineral textural characteristics, and their impact to metallurgical processing. On the map to the right, we sampled a range of pegmatites in the Yilgarn and Pilbara cratons, including the well-known Greenbushes deposit, 350 kilometres south of Perth, and Mount Catlin, just out of Ravensthorpe. Around the Kalgoorlie area, pegmatites included Bald Hill, Mount Marion, Home North and the Sinclair Cesium deposit just to the south of that, and older workings out at Lepidolite Hill. Further to the north, drill core from Kathleen Valley and Dalgaranga was sampled. Finally, in the Pilbara Craton, core was sampled from the Pilgangoora deposit during, at the time, operations by Altura Mining. And here you can see a very nice example of one of the LCT pegmatites examined in the study. The elongated subparallel greenish crystals in the sample, the lithium-bearing phase spodumene, in a quartz albite muscovite matrix. In Australia, most of the lithium resource is found in WA, with pegmatites belonging to the lithium, cesium, tantalum, or LCT pegmatite family. Lithium occurs as the lithium pyroxene spodumene, with about 8% lithium. However, there are other important lithium minerals, as you can see in the table in the top right, including petalite and lepidolite. It's a series of lithium-bearing micas, and a nice example of which is shown below here. Globally, other important lithium sources include the low-grade salars in the image at the bottom right there, in South America, such as Argentina, Chile, and Bolivia, and lithium clays, such as hectorite, smectite in Mexico and Nevada. Falling within the scope of the geology module of the project, uranium-lead laser ablation geochronology determined similar to near identical ages of 2643 to 2629 Ma for pegmatites from Greenbushes, Pilgangoora, Dalgaranga, Bald Hill, and Londonderry. This is consistent to published ages for other WA pegmatites. However, the grain size and low uranium contents of generally less than 100 ppm of zircon indicate that these are inherited and did not form in the pegmatite. This puts a maximum age constraint on the timing of pegmatite crystallization, as pegmatites must be younger than their host rock. The older revised age for Greenbushes, and we can see the Concordia plot at the right there, means we can more confidently suggest a genetic link to the Logue Brook granite at 2612 Ma, which was previously suggested as the parent granite source of the Greenbushes pegmatite. However, shrimp analysis is required to refine the zircon age before a genetic link can be confirmed. Recent work has suggested a correlation between peak periods of pegmatite emplacement and increased crustal magmatism associated with cycles of supercontinent breakup and formation. The plot on the right shows a frequency distribution of pegmatite ages in major global pegmatite fields, as shown in red, and granite ages in grey. LCT pegmatite ages measured in the current study coincide with assembly of the Sclavia Superior Kennelland supercontinent, as you see boxed here. In this plot, the red star denotes the similar age of the well-known giant Tanko in Canada and Paquita in Zimbabwe pegmatites. In the Yilgarn, the 2650 to 2600 MA interval correlates with the formation of low calcium granitoid melts accompanied with the intrusion of mantle-derived atachitic granitoids. One of the observations that struck us was the very common alteration of spodumene in the LCT pegmatites we examined. Alteration can be grouped into three main types: pseudomorphic replacement, graphic textured alteration, and vein infilling. The last two examples affected all of the LCT pegmatites included in this work. To the right, the image shows an example of the pseudomorphic replacement of spodumene. The large mottled green-black crystals you see here were once spodumene, but have been completely replaced in situ to an assemblage of secondary fine-grained clays and layered silicates. Now we'll take a look at examples of each of the alteration types in the next few slides. In this example of the pseudomorphic alteration style, the photograph to the left shows a large spodumene crystal with the dark alteration band about the crystal margin. The yellow dashed line shows where the sample was cut to prepare a polished mount for analysis. This is shown in the automated false color mineral map to the right, where the different phases have been colored up. Spodumene is shown at the bottom of the image in green. About the crystal margin, the alteration was mapped as a mixture of secondary lepidolite and a magnesium phase. However, the mineralogy was confirmed by XRD analysis as consisting of a mixture of mica as secondary muscovite and a lithium chloride phase, cookite. You can see the fine-scale nature of alteration as veins penetrate the crystal interior. This is shown more clearly in the potassium distribution map below the mineral map. This type of alteration progresses congruently inwards until the spodumene is completely replaced in situ. As you can see an example here where that has happened with this large spodumene grain crystal being completely replaced. Now, the white dashed line in both the mineral map and the potassium distribution map we interpret to mark a muscovite decomposition front. During pegmatite alteration, muscovite is decomposed, releasing potassium, which in turn is incorporated during alteration of spodumene to form secondary potassium-bearing clays. Alteration progresses inwards along crystal fracture surfaces and cleavage planes until completion. As well as introducing potassium, alteration also introduces minor amounts of magnesium and iron in the secondary assemblage, suggesting the influence of an external fluids source with contributions from mafic and ultramafic country rock. This type of alteration is inferred to be post-mineralization of the pegmatite and occurs at a much later stage. Here we look at the graphic texture and vein alteration styles. In the top images, the graphic alteration involves the development of a microscopic graphic textured quartz spodumene intergrowth, where spodumene is in contact with feldspar, mainly as albite, but in this case here with K-feldspar. The top false color mineral map and silica distribution map clearly show the graphic textured alteration along the grain margin of spodumene in contact with feldspar. Alteration results in the overall loss of aluminium and lithium and is interpreted as a re-equilibration or replacement reaction in the later stages of cooling of the pegmatite. The two bottom images show an example of the almost ubiquitous vein alteration observed in spodumene. Such veining is generally not visible to the naked eye and in the mineral map is variably identified as a mixture of secondary micas, lepidolites and so on, which can be described as sericitic in nature. The distribution of the vein network is more clearly shown in the potassium distribution map, shown here, which shows that veining mainly occurs along cleavage planes and fracture surfaces. So together, alteration decreases the lithium grade of the pegmatite, that is the lithium in spodumene. Alteration introduces element contaminants such as potassium, magnesium, iron, and rubidium, and mineral impurities as inclusions. We'll look at how this affects the processing of spodumene in the next few slides in relation to the general pegmatite extraction and recovery process flowsheet used by producers, as shown in the image on the right. Here we'll be looking at the beneficiation, calcination, and sulfate roasting stages of the process. After crushing the ore, one of the main separation techniques to remove gangue phases such as quartz, feldspar, and mica from spodumene exploits the difference in the physical properties of these minerals, namely the difference in their density. Spodumene has a density of about 3.1 to 3.2 grams per cubic centimeter, whereas the main gangue phases have a lower density in the range of about 2.6 to 2.8. So on the right-hand side, you can see an example of an albite spodumene pegmatite. This was crushed, sized, and polished mounts prepared of the different size fractions for automated mineral mapping, with a false color mineral map of a coarse fraction shown in the main image. From the mineral mapping, we can extract information on the mineral abundance in the sample and mineral locking properties of spodumene. The bar graph shows the proportion of free spodumene and minerals locked within spodumene with decreasing particle size. While spodumene is mostly liberated in all the size fractions, up to 20 to 25% of the spodumene grains contain intergrowths or inclusions of quartz and feldspar in the coarse fraction. And even in the finest fraction, still there's about 10% of inclusions and intergrowths within spodumene. There is also evidence of graphic alteration of spodumene where feldspars are in contact with spodumene. Such alteration in the presence of mineral impurities within spodumene decreases the grain bulk density. This impacts the recovery of spodumene in dense media circuits, as the spodumene will float and go off into the tails. We'll now look at the impact alteration has during the processing calcination stage. Spodumene, as the monoclinic alpha form, undergoes thermal transformation to the tetragonal beta form in the temperature range 950 to 1100 degrees. The image on the right shows the reaction pathways during heating, which can form an intermediate gamma spodumene phase depending on the rate of heating. Transformation of alpha spodumene to beta spodumene is necessary, as the beta spodumene phase has a more open, less dense crystal structure. This makes it more amenable to acid leaching, and therefore lithium is more easily extracted during the leaching stage. During calcination, other mineral and alteration impurities may also undergo thermal reactions. The graph on the right shows the loss in weight as the dashed curves and thermal reaction curves as the solid lines of various minerals in pegmatites against the temperature on the x-axis. As you can see, the primary muscovite and the altered mica products, or cerussite, undergo dehydration and melting reactions at temperatures just before or coincident to the zone of spodumene transformation, shown by the shaded box here. Feldspars may also be affected and can undergo partial melting above about 1050 degrees. This next slide shows the changes in mineral textural features associated with calcination as temperature increases. The image on the right shows backscattered image and TEMA image pairs calcined at 950, 1050, and 1100 degrees. At 950 degrees, alpha spodumene is still intact and has not yet transformed to beta spodumene. However, TEMA imaging has mapped the initial formation of mica melts in blue along a major cleavage fracture surface. As the calcine temperature increases, spodumene transformation progresses, with the spodumene becoming more fractured, porosity increases, and the formation of mica melt increases, with the fluid flow textures such as vapor bubble casts also forming, as you can see here. The mica melt forms amorphous glassy coatings along internal surfaces that effectively encapsulate and quarantine spodumene from acid leaching. This reduces the amenability of beta spodumene to acid leaching and inhibits the recovery of lithium. Finally, evidence for the refractory effect the formation these glassy melts have is shown in an example of calcined spodumene. A sample of spodumene was calcined and subjected to sulfate roasting and leaching under conditions that simulate what happens commercially. The leached spodumene residue was then characterized and element distribution mapping performed using high-resolution time-of-flight secondary ion mass spectrometry, TOF-SIMS, which is capable of mapping very light elements such as lithium. The upper backscattered image shows the main textural features of the region of interest examined by TOF-SIMS. It is thought the manganese and iron oxides in the backscattered image, and as shown by the element mapping, formed by the exsolution of iron and manganese incorporated in spodumene, and possibly mica, during calcination. TOF-SIMS element mapping shows evidence for the presence of glassy melts from the lithium and sodium distribution maps, which surrounds regions with relatively high lithium contents of unleached spodumene. These glassy coatings are resistant to sulfuric acid and inhibit the leaching or removal of lithium. Lastly, from the comparative analysis of the ore types identified in 10 pegmatite fields throughout WA, a practical geometallurgical model was developed intended as a benchmarking tool to identify factors inherent in different ore types that either favour or limit the recovery of lithium. The benchmarking model covers the major issues and impediments to treating pegmatite ores and includes solutions to address specific effects of mineralogy, taking into account specific details of the equipment used to process lithium ores. The 4 key factors to selecting the appropriate ore treatment option are the lithium mineral host, is it spodumene versus petalite or mica, grain size of the lithium host, is it coarse-grained or fine-grained, impurities such as iron and manganese, and mineral textures, associations, and alteration. So this work effectively demonstrates that ore body knowledge and geometallurgical characterization provide the fundamental link between geology and the efficient processing and recovery of lithium. So if you want to find out more about WA's pegmatites, the M532 report is now available through GSWA's e-bookshop. Please check it out, and if you have any questions and would like to get in touch, please don't hesitate to contact me. Thank you.